Let's learn about SQL indexing. In this session, we'll explore how indexes can dramatically improve the performance of your database queries. Database indexes are similar to a book's index. They are special data structures that improve the speed of data retrieval operations on a database table. Indexes allow the database to find specific rows in a table without scanning the entire table. However, there's a trade-off. While indexes make reads faster, they can slow down write operations such as inserts, updates, and deletes, because the index also needs to be updated whenever data changes. Let's compare a database query with and without an index. Without an index, the database must perform a full table scan to find the matching rows. For example, to select all users with the last name Smith, the database scans every row in the table. With an index, the database can quickly locate the matching rows using the index. You can create an index on the last name column of the users table. The database will then use this index to directly access the rows where the last name is Smith, significantly speeding up the query. The B-tree is the most common type of index used in relational databases. It's a self-balancing tree data structure that maintains sorted data, allowing for efficient searches, insertions, and deletions with a logarithmic time complexity, often denoted as log n. Because the data is kept in a sorted order, it is efficient to use range-based queries. There are several types of indexes. First, a single column index is created on just one column of a table, often used for primary keys, unique constraints, or frequently queried columns. Next, a composite index is created on multiple columns, where the order of the columns matters. These are useful for complex queries that filter based on multiple conditions. A clustered index physically reorganizes the table data in the order of the index, and is often based on the primary key. Finally, a non-clustered index is a separate structure that points to the data within a table. Non-clustered indexes are secondary indexes and improve the query performance without reorganizing the data. Indexes can be created by using SQL. A basic index is created using the createIndex statement, followed by the index name, the on keyword, the table name, and then the column in parentheses. To ensure all values in the index column are unique, a unique index can be created. A composite index, covering multiple columns, can also be created. When creating a table, an index can be defined as part of the table creation statement. Key index options include unique, to ensure unique values, ASC or desc to specify sort order, with ascending being the default, and include, which is used in SQL Server to add non-key columns to the index. A common naming convention is IDX_table name_column names. When creating indexes, consider the existing table data volume because creating indexes on large tables can be resource-intensive. You might also use the online option for production environments if it's available, to minimize disruption. To analyze your queries, use the explain statement before your select statement. For example, explain select asterisk from customers where last name equals Smith. The explain statement reveals how the database uses, or doesn't use, indexes. When the database uses an index, it will show index scan or index seek, whereas without an index, it will show table scan or full table scan. Here's an example explain output. The key shows IDX_last name, indicating that the index is being used. The type is ref, showing a non-unique index lookup. The rows show 12, which estimates the number of rows that need to be examined. Indexes are used when the query pattern involves filtering directly on an index column, such as where index column equals value, or when using like with a prefix or between or in. Indexes are not used when using like with a wildcard prefix, or when applying a function to the index column in the where clause. Some tips for query optimization. Put index columns directly in where conditions. Remember that the column order matters for composite indexes. Be cautious with or conditions as they may need separate indexes. Monitor query plans for production workloads, and consider function-based indexes for complex conditions. Indexes have several benefits, the primary one being faster query performance. They dramatically reduce search time, changing it from O of n to O of log n. Also, indexes improve sorting by eliminating the need to sort results when using order by on indexed columns. In addition to these, indexes provide better server resource utilization by reducing the number of input, output operations and CPU usage for query execution, and enforce constraints by using unique indexes to ensure data integrity by preventing duplicate values. Despite these benefits, there are some trade-offs. A storage overhead is incurred since each index requires additional disk space, typically 10 to 20% of the table size. Slower write operations happen because insert, update, and delete operations take longer, since the indexes must be updated as well. Also, index maintenance is necessary as you need to monitor and rebuild or reorganize indexes periodically. And finally, there is the risk of too many indexes. Excessive indexes can overwhelm the query optimizer and slow performance. It's important to maintain indexes. Over time, indexes can become fragmented and less efficient due to data modifications, such as inserts, updates, and deletes. To monitor your indexes, check fragmentation levels periodically, review index usage statistics to identify unused indexes, and monitor query performance for degradation. Pay special attention to tables with high write activity. There are several maintenance tasks. Rebuilding recreates the index completely, either offline or online. Reorganizing defragments the leaf level of the index tree. Updating statistics refreshes the statistics used by the query optimizer. And dropping unused indexes removes indexes that aren't being used. Here are some index best practices. Target the right columns by indexing columns used in where, join, order by, and group by clauses. Prioritize columns with high selectivity. Remember that column order matters, so put equality filters first in composite indexes, followed by range filters. Covering indexes can improve performance, so include all columns needed by the query in the index using the include clause to avoid table lookups. Don't over-index, as too many indexes can slow down writes and confuse the optimizer. Always test thoroughly by benchmarking before and after adding indexes, and using explain to verify that the database is using your indexes correctly. Finally, monitor and maintain your indexes by regularly checking index fragmentation and usage statistics. Remove unused indexes and rebuild or reorganize them as needed. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.